Okay. This proof I put together on Illustrator. I know that seems kind of weird, it's a little wonky, but that's the program that I'm used to using, so bear with me here. I'm going to assume that you understand what prime numbers are and have some understanding of natural numbers, sets, and a few other basic mathematical concepts like that. Starting out, we know that the set n, forgive my cursor here, it's a little pencil, that's because it's Illustrator. We know that the set n containing natural numbers is infinite, or more accurately, that the set of natural numbers has an infinite cardinality. Prime numbers, right here, are a subset of n, and it also has an infinite cardinality. This all has already been proven. I'm just making the point. What does it mean? How do we look at this, and how do we understand it better? Here we have a number line, which is where we're going to start. From left to right, starting at 1 and continuing on to the right forever, infinitely. Now, we have to look quickly at numbers and what different numbers mean. They can represent different things. Cardinal numbers are numbers as amounts. Ordinal numbers are numbers that put things in order. For example, 9 is before 10, but it's also after 8. There's an order to it. And then bear with me here. I invented this term, frequential numbers. These are numbers as frequency. And for the purpose of this proof, I don't have a better name. That's just what I came up with. It's a silly name, but it just suggests that numbers can indicate frequencies. Here's what I mean. Here you have the number line, natural numbers, and laid over that is 2 as a frequency. So what we're really looking at here is that every other number is divisible by 2. Now there's no big surprise here. It's basically just division, but it's a way to lay it out so that we can understand it, hopefully better. 2 has a frequency of 2. No big surprise there either. Moving forward, here is number 3 laid out as well. You can lay these out on a sort of graph or chart where you're comparing numbers as frequencies against natural numbers. 3 has a frequency of 3, and sometimes the 2's and the 3's line up, and other times they don't. Now I've added numbers up to 6 on the vertical line and out to 25 on the horizontal. You can even turn natural numbers along the bottom into the frequency of 1, because that's basically what that is. And we are going to call these stacking frequencies. What we've done is stacked these numbers as frequencies all on top of natural numbers or just the 1. What's the point? Why do we do this? Basically, it's nothing more than an expanded multiplication or division table. Not fancy, nothing new, but if we look at it closely, it's actually a little bit more important than that. What this table shows us is that there are very rigid patterns to division as they relate to natural numbers. Calling these stacked frequencies, and here are those patterns. This is the 3's and the 2's. You can see that the 2 and 3 pattern illustrated here with these pink lines are repetitive. They're the same. They go out to infinity. There's no reason to believe they don't. On top of that, we can add, excuse me, bear with me. you can add the pattern for 4. And as you can see, it's the same basic shape as the pink pattern. And you can also see that each larger pattern requires a specific number of small patterns before they line up. For example, here is the 4 pattern. It's down, up, across, and a vertical. And inside that pattern is 2 of the 2, 3 patterns. And that's true over and over again. And if you were to draw this out and include these larger numbers, you would see that it takes a certain number of the 4 pattern to make up the 6 pattern, and so on and so forth. They're sort of like fractals. They just keep getting bigger, going off this direction. Problem here is that this gets very big very quickly. It's very wonky, and it's not particularly helpful by itself. So what I'd like to do is take a step back to this, 2s and 3s. What we establish in this table is that aside from the numbers 2 and 3 themselves, prime numbers can only appear to the left and right of a multiple of 6. Here's a multiple of 6, and this, left and right, are the only places that prime numbers can exist. They can't exist anywhere else. And that is because all the other numbers are, except for 2 and 3, are divisible by either 2 or 3. Again, this is nothing new. I'm not trying to tell you I invented this. It's just a helpful, interesting way to lay it out so that we can see why that is and sort of remind ourselves that that's the truth. Six is divisible by 2 and 3. 5 and 7, left and right. Those are prime numbers. I'm not trying to tell you that 2 and 3, that any number left and right of a multiple of 6 is a prime number, because that's not necessarily the case. 25 is not a prime number, but it's to the right of a multiple of 6. All we're going to say here is that these are possible primes. All the other numbers, it's impossible for them to be primes, except for 2 and 3, which we're going to exclude. You're going to have to humor me for a second here. Going forward, I'm just going to exclude 2 and 3 and set them aside. We can agree that they're prime, but that they don't follow the rules of the other primes. So we can call them super prime or something like that. And just from now on, remember, 2 and 3 are not included in this discussion. So what we really have is a set of natural numbers. A subset of that is the possible primes. These are all the numbers that are not divisible by 2 or 3. They include primes, and they also include some non-primes. And then a subset of that is the primes. So what do we do with possible primes? What's the point? We still have this big table comparing frequency to natural numbers, and it's not any less complicated or wonky. What do we do? Well, here is what we do. What we can do is distill this all down and get rid of all the information we don't need. Lose all the stuff that's either repetitive or numbers we know aren't prime for sure. We make a list. Here's what the list looks like. The n, this number or this column, down the center are the multiples of 6. So the first one is 6. The second multiple of 6 is 12, 18, 24, etc., etc. Goes on. The number to the left and to the right of these centers, we're going to call these the centers. The numbers to the left and to the right of the centers are the possible primes. They are the multiple of 6 minus 1, so 6 minus 1 is 5, and they are the multiple of 6 plus 1. 6 plus 1 is 7. Okay, centers and the left and the right. That's true all the way down. This goes on infinitely. It just keeps going on and on and on. And it's very structured, which is interesting. And what you can do with this list this way now is cross out all the numbers that are non-primes. And here are all the multiples of 5s that have been crossed off the list. 35, 25, 55, 65, etc. Keeps going down. The interesting thing here is if you draw the line between 35 and 25, the center are also multiples of 5. The problem here is that we're still doing math. If we want to do this again, we have to go through the list, do the division, find out what's not prime, figure out what else is not prime, try to draw a line, see where we get. How do we get away from the math? As it turns out, if you extend the pattern backward up into negative numbers and do it opposite, what you can do is establish your first cross line to sort of show you how this is done. If you draw the line between 5 and 5, what you do is you cross 0, but you establish the angle, and then all you have to do is drop this down every 5th center, and you've crossed off all the 5s, the multiples of 5, off this list without having to do any math. We can do the same with 7, and then drop it down every 7th center to get rid of all the multiples of 7, like this. That's true for every single number. The only difference is that every pair has cross lines at increasing angles. The angles get steeper. Here's 11. We drop them down. And you can just keep doing that infinitely. It just goes on and on. What you're left with, in theory, is only numbers that are prime. What you don't count is this first line. Obviously a 5 to a 5. We're not crossing off the 5. This is the establishing. Any of the lines that cross this 0 here, you're just establishing the line before you drop it down. So what you have on your list here is 5, 7, 11, 13, 17, 19, 23. The first non-prime on this list is 25. It keeps going on and on. Okay, so because each of these sets of cross lines is based on a set frequency, when you compare to each other from the starting point of 0, they'll drop in and out of phase. They don't just share the center of 0. Eventually they share centers again. And here's an example. This is 5 and 7 sharing 35 as a center. And you can see right here they share it. These are multiples of 7. These are multiples of 5. And they both converge at 35. You guessed it, 5 and 7 is 35. So what we're establishing here is a couple important points. First, multiplying possible primes together will give you this common center for their cross lines. Second, cross lines that do share a common center are unable to cross the adjacent possible primes off the list. So these two, because their center is at 35, they cannot cross off 209 and 211. These will be important in 1 minute. Here's an example where 5, 7, 11, and 13 have all been multiplied together to get the common center of 5005 down here. You can see here that the possible primes, except for those adjacent to the common center, these two, have been crossed off the list. These are all non-primes. And you can do the math here. You don't have to trust me. This works. This is their common center. They're unable to cross these two off the list. And I'm not trying to tell you that this is a twin prime. Either one of these could be non-prime. I'm just establishing the fact that at this point, none of these cross lines can touch this, what would be a horizontal line here, these two. I hope that I've explained all of this clearly to now, because I'm going to throw this graphic at you. And I'm going to try to explain it to make it make sense. This kind of condenses everything that I've brought up to this point. NP sub p, this, is the multiple of 6 that is the product of all possible primes. It is an infinitely large number. This is all possible primes multiplied together. All of them. PP1 and PP2 are the possible primes that are adjacent to that center. They cannot be touched by these cross lines. They're also infinitely large numbers. Just because this number is basically infinity, these two are also infinity. Infinity plus 1 and infinity minus 1. The pink X's represent the cross lines sharing the common center of NP sub p. And the infinity symbols at the bottom and at the top show that these cross lines extend on forever. They don't stop. Now, what does this mean? That's the whole point here. Interestingly, because of all this, there is no set of cross lines that can touch twin prime PP1 and PP2 when they share the center in PP. When you multiply all possible primes together, you get the common center of NPP, and none of those can cross that, what would be a twin prime, off the list, suggesting that twin primes just go on forever and ever. Because we've multiplied all possible primes together and their cross lines have converged at a common center here, all possible primes have been crossed off between the common center and infinity. So you've crossed off, because this includes all possible primes. We have all combinations of cross lines. We've crossed off every single line, every single number between this center and infinity. In other words, all of the possible primes between this center and infinity are non-prime, which means the distance between primes can be infinite. There are a number of other ideas that this theory suggests. For example, I believe this doesn't actually prove that the infinitude of twin primes, but rather proves that you can't prove the infinitude of twin primes. I know I've dropped a lot here. Some of you probably think it's ridiculous, but I'm going to leave it at that. Feedback is welcome. Thanks for watching.